We now take this problem of problem 62 of your textbook. It says that a small block of super dense material, and whatever it is, its mass is 3 into 10 to the power 24 kg. That is why they have given the adjective super dense. Is situated at a height h, which is much, much smaller than r, that is Earth's radius. That means that is near to Earth, although it is very, very heavy. From where it falls, that means it just falls like any stone falling on the Earth's surface, as simple as that. But the speed of that super dense material at the time when its height from the Earth's surface has reduced to h by 2. Its original height was h. It has dropped half the distance. The mass of the Earth is given. Now, to solve the problem, let's draw the diagram. Let us say this is the Earth, and say its radius is r, and mass of the Earth is 6 into 10 to the 24 kg. So we write the mass of the Earth is equal to 6 into 10 to the power. At this time, the small block, also it is not very light. Its mass, if we write small m, its mass is 3 into 10 to the power 24 kg. The first thing that should come to your mind is that small mass is equal to the mass of the Earth divided by 2. Just half the mass of the Earth, or capital M by 2. And this body is at a height h. Drops from h, it drops from here. And when it comes to h by 2, at this time, what is the velocity of this? This they want us to find out. At any moment during the fall, you can write this at any moment the fall or during the motion, the linear momentum of the small body and the linear momentum of the Earth will be same in order to maintain the law of conservation of momentum. At any moment during the fall, from the conservation of momentum theory, we find capital M into velocity of the Earth is equal to M and velocity of the body. Velocity of the Earth, say Earth also moves upward with a velocity v. As such, the Earth should not move when something falls on it. But here, the mass of the body, smaller body, is half of the mass of the Earth. So it will create a movement. From mv, or we can write capital M velocity of the Earth equal to capital M by 2 into. From here we get velocity of the earth is equal to velocity of the smaller body. Velocity of the earth is velocity of the smaller body v divided, right? Now, when the small body falls from h to h by 2, then the small body falls from h to h by 2, then it gains the potential energy. It's, sorry, it loses the potential energy. H by 2, it loses potential energy of is equal to potential energy of m g. So this small m is equal to capital M by 2 g by capital M g a, loses this potential energy. By this loss of potential energy, it gains the kinetic energy. And it gains kinetic energy is of m and v square. This is equal to half m, small m is capital M by 2, v square equal to half m v square is equal to capital M square by 4. But here is a very special case where Earth also moves. So Earth also gains a kinetic energy. Earth also moves and gains a kinetic energy is equal to half m and velocity of the Earth square equal to capital M by 2. Velocity of the Earth we have already found small v by 2. So small v square by v square by 4 is equal to capital M v square by 8. M v square by 8. Right? Now, this energy equation has to be equivalent because energy lost by the small body is this amount. Energy, kinetic energy gained by the small body is this amount, and kinetic energy gained by the Earth is this amount. So the loss of kinetic energy, so this mgh by 4, h upon 4, kinetic energy gained by the small body, that is equal to m v square by 4 plus m v square by 8. This is equal to p by 8 capital M v square From here we get, sorry, this was, uh, this was capital MGH. I made a mistake, this small mistake, this was capital MGH. This value was capital MGH, capital MGH. So capital MGH is P by 2 capital M V square. Now this capital M cancels. So what we are left with is square is equal to 3. Therefore, velocity of that small body, velocity of that small body is 5. This is the answer, right? Now we shall go to the next question.